Hello, my name is Teo Rodriguez, and today we're going to convert binary numbers to decimal numbers and vice versa, as well as determine the importance of IP addressing in networking system and its subnet mask, and identify the network portion and host portion of an IP address. So let's just jump right into it. So for our first numbers, set of numbers, we have 201, 17, 29, 4. This is our IP number. To convert this, we have to split them into four numbers. So first, we're going to convert our first number here, which is 201. In order to convert our numbers, we have to place down powers of 2s that we can subtract to this number. So first, we have 128, 64, 32, 16, 8, 4, 2, and then 1. We're going to circle this since we can subtract it. So now we can subtract 201 to 128. 201 minus 128 is 73. So we can go ahead and add this here. And then we can subtract 73 to 64. 73 minus 64 is 9. And go ahead and add that. And then we can subtract 9 to 8. 9 minus 8 is 1. Add this as well. And 1 minus 1 is 0. So now that we have these numbers here, we can now convert it into binary numbers. So to do that, all the circled numbers here will be converted into 1, while the others will be converted into 0. Okay, let's go ahead and do that. So this is circle, this is 1, this is circle, this is also 1. This one is not circle, so both of these numbers are 0. This one is 1, these are zeros, and then 1. So now we have our first set of binary numbers here. We're going to go ahead and do that to the rest of the numbers here. So for 17, we have this set of numbers. So first we can subtract 16, so we're going to circle this 16. 17 minus 16 is 1. So 1, we can subtract 1 to 1. 1 minus 1 is 0. So we can now convert it 0, 0, 1, 0, 0, 0, and 1. Also, since we're going by 8 bit, we're going to add another 0 here. So we'll have 8 bits in total. So for 29, we're going to subtract 29 to 16. So 29 minus 16 is 13. And 13 minus 8, we have 5. So we can go ahead and put this here. And 5 minus 4 is 1. And 1 minus 1 is 0. Let's convert these into binary. This is 0, 0, 0, 1, 1, 1, 0, and 1. So for it's simple, we're going to subtract 4 to 4 itself. So 4 minus 4 is 0. We only have 1 in this set of numbers. So 0, 0, 0, 0, 0, and then 1, then 0. So now we can combine all the binaries that we've converted. So this is 1, 1, 1, 1, 0, 0, 1, 0, 0, 1 from 201, and then 0, 0, 0, 1, 0, 0, 0, 1 from 17, then 0, 0, 0, 1, 1, 1, 0 from 29, and then 0, 0, 0, 0, 0, 1, and 0, 0 from 4. So 201, 17, 29, and 4 is equal to 11001, 001, 001, 0001, 00011, 010000000, 100 binary. For the second one, we're going to solve it in my slideshow. I went ahead and made it into a slideshow, so we're more efficient with our time. So we have 192.168, 1.1. For 192, we solved it like this. 192 minus 128 is 64. 64 minus 64 is 0. So now we have 1, 1, 0, 0, 0, 0, 0, 0. For 168, we have 168 minus 128. We have 40. 40 minus 32 is 8. And 8 minus 8 minus 8 is 0. So we have 1, 0, 1, 0, 1, 0, 0, 0. And for the ones, we just have to subtract it by itself and put zeros before our 1. So this is what we got for each numbers. So when we add it all, we have 1, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 1, 0, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, and 0.0.0.0.0.1. For the third one, we have 172.0.0.0. For 172, we solved it like this. 172, we have 128. 172 minus 128 is 44. Minus 32, we have 12. And 12 minus 8 is 4. And 4 minus 4 is 0. The circles, we have 128, so that's 1, 0, 1, 0, 1, 1, 0, 0. For 0, we have as is. There is as is, just like number 1, the one we have earlier. You don't have to do anything but add 7 zeros before it. So this is what we have for 172. 172 is equal to 1, 0, 1, 0, 1, 1, 0, 0. And for the zeros, we have 8 zeros for each. So we have 1, 0, 1, 0, 1, 1, 0, 0, and 8 zeros each. And yeah. So now we're going to solve for this binary numbers. And we're converting it to decimals, the opposite of earlier. So first, we're dividing it into 4 groups, like we did with the decimal numbers. The first one, for 11001110, we have to place the corresponding power of 2's, like this. 2 to the power 7 is equal to 128. 2 to the power 6 is equal to 64. 2 is 0, since there's 0, and 8, and 0, and then 2 to the power 3, which is 8. 2 to the power 2 is 4. 2 to the power of 1 is 2. 2 to the power of 0 is 1. Actually, we actually have to multiply this by 1, but since it would equal to itself, and I just simplified it. So 128 plus 64 plus 8 is 4 plus 2 and plus 1 is equal to 207. For the next one, we have 0, 0, 0, 0, 0, 1, 1, 0 plus 0, 0, 0, 0, 0, 0, 2 to the power of 1, 2, 2 to the power of 1, 2 to the power of 0 is equal to 4 plus 2 plus 1 is equal to 7. For the next one, we have 0, 0, 0, 1, 1, 0, 0, 0, 1, 0. These are all zeros, plus 2 to the power of 1, plus 2 to the power of 3, and 2 to the power of 1, which are 16, plus 8 plus 2, which is equals to 36. For the last one, we have 101000000, which corresponds to 2 to the power of 7, plus 0, plus 2 to the power of 5, and the rest are zeros, so what we have 128 plus 32 is equals to 160. So these binary numbers is equal to 207.7.46.160. This is our IP address. Our given address is 192.68.1.1. Our subnet mask is 2.255.255.255.0, which is the default for most of the time. For our first question, what is the network address in binary? For the network address 192.168.1.1, we converted each decimal into its 8-bit equivalent, like this on the screen. The result is 11000000. I'm not gonna say it all, but each section of the IP address is called an octet and is always represented by 8 bits. For the next question, what is the subnet mask in binary? So this is our subnet mask 2.255.255.255.0. So in binary, it becomes like this. The ones here are the network portion, while the zeros they represent the host portion of the IP address. For the next question, what is the prefix length? The prefix length contains 24 consecutive ones in binary. So yeah, it should be written as /24. I forget the slash, but it should be /24. And for the last question, in the network address 192.168.11, underline the network portion and encircle the host portion. Our network portion here, 192.168.1. Those are the first three numbers in the IP address. These are the 4 octets. The last octet right here is the host portion. This means devices on the same network share the first 3 octets, and the last octet is uniquely identified by each device. So here is our answer right here. So for our actual questions, here's the first one. Why do we need to convert decimal values to binary numbers? So we convert decimal values to binary because computer understands and processes data using only 2 digits, which are 0 and 1. So converting IP addresses into binary allows our computers and networks or networking devices to identify network and host portions. perform subnetting, and communicate accurately. And for our second question, why do all computing devices have an IP address? Is it possible for n devices to have the same IP address? Explain your answer. Every computing, I guess every computing device needs an IP address, so we can identify it and communicate with other devices or networks using our devices. So two devices on the same network should not have the same IP because this causes an IP conflict, and so this makes our communication unreliable or prevents one or both devices from connecting properly. And for our third question, what is the importance of the subnet mask? Um, Subnet mask is important because it identifies which part of an IP address is the network portion and which part is the host portion, like we did earlier. This helps routers and other network devices determine whether data should stay within the local network or be sent to another network. So for our third and final thing, what can we conclude from this activity? So what we can conclude from this is we now know how to convert IP addresses between decimal and binary and determine the network and host portions. So the first three portions of an IP address is always the network portion, and the last one is always the host portion. And then we also understood the importance of IP addressing in computer network. So this is essential for figuring out or configuring networks and ensuring devices communicate correctly. Thank you so much for watching. I'll see you on the next laboratory exercise. Bye bye.